now will be floating like this. I'm interested what happened to buoyant force in this case and earlier. So there's a container at rest. Now the container is accelerating. Now instead of this next third case, I'm going to spin this container about its axis. Can you remember? We have discussed earlier previous classes rotation of this one. So how the free surface will align itself. Okay, let this be the axis about which it is rotating. So here that object is here. Okay, let some x3 length be immersed here. So there's a density of solid. Same solid. So what will happen to the buoyant force and what will happen to wall, like a length of the solid immersed here? It's a cube. Everywhere I'm saying it's a cube only. Cube of side length L. Let's analyze one by one. Let's come for first case. So what are the forces buoyant force? FB1, I'll write it. Weight of the solid. So what is the buoyant force is equal to? Density of liquid, volume immersed, V1 into G. Density of what is volume immersed? A into X1 or L square X1 into G. And now container accelerates. Then the buoyant force now will not act vertically up. It will act always. So better select effective buoyant force. Effective buoyant force. So what are the other forces that are acting like? The weight mg, then pseudo force. So the resultant force, how it will act? It will act opposite to buoyant force. So against the effective weight, the buoyant force will act here. So what is FB2? FB2 should be equal to no. So the effective of this will be root of mg whole square plus ma whole square. So this should be m. This is due to equilibrium. Okay, I think some of your confusions are why you are not writing definition. And it's in equilibrium. And it will act opposite to the resultant force, like the inertial force ma and the weight in that one. So let's go for the basic definition of buoyant force. Density, volume immersed, L square x2. Effective will be root of g square plus a square. Effective g, I should write effective g, or still if you're getting confusion, write g effective. Or volume immersed. I think I'll bring in order. No. What is volume immersed? L square x2. G effective is how much? Root of g square plus a square. I agree. I think nobody is having any problem. What is x2? Length immersed in this case. What is our question? What about x1, x2? All those things we have to check it. Let's go back to the definition. Let's go back to the definition. What the definition says? The length immersed, please all of you look it here. I just brought you back. The length immersed depends on what? Depends only on the density of solid to density of liquid into height, no? Or the fraction of length immersed, x dash by h. It is independent of gravity, will I agree? One more, I think there's a better formula. There's no gravity in the picture, no? So it just depends upon the density of solid to the liquid into the height. So therefore here, the length immersed is independent of acceleration of the container, acceleration of the liquid. So with this, what shall we write here? Is it x1 equal to x2? Yes, buoyant force are different. Definitely you can say buoyant force are different. but x1 must be equal to x2. The reason for that, this length immersed is independent of acceleration of the liquid or acceleration of container. Okay, let's come for here. How the buoyant force? So what are the forces that are acting here? The buoyant force will act like this. FB3, weight of the solid. Pseudo force, m omega square r. At what distance it is? At a distance r. Can you remember this one? So let's write now FB3 minus root of or mg in equilibrium. So therefore this will be is equal to m root of g square plus omega square r whole square. Now what is the basic definition of buoyancy force? Equal to rho L volume immersed into G effective dash. It's some other effective G, no? So G effective dash will write it. So this will be rho L V3. What is G effective? G square plus omega square R whole square. What is volume immersed here? Rho L L square X3 no. Let's do one thing. What will be that volume immersed? I'm interested only this volume immersed. I'll just shade it yellow. There is a volume immersed. It will be same because volume immersed just depends upon the fraction of volume immersed is independent of the acceleration of the liquid. So therefore, first will as we know that. This is very important. See, we do many problems like where container accelerating. So don't get scared. You need to bother much. You have this idea in front of you. The fraction of length of solid immersed in liquid is independent of acceleration of container. I'm just putting a statement. So therefore, what do I can write? X1 equal to X2 equal to X3. But don't say buoyant force. In fact, what you can say, FB1 not equal to FB2 not equal to FB3. Volume immersed is independent of acceleration of fraction of length immersed, fraction of length of solid immersed, or directly volume immersed is independent of acceleration of container. I think this is going to really help us a lot. How to calculate the effective buoyancy? The effective G. Since like x1 equal to x2, so therefore what we can write? Even volume immersed is also same. So volume immersed is independent of, or fraction of volume is immersed is independent of acceleration of container. So like this, what happen? We'll make a rule. I just wrote what? G effective. I think that is enough, no? So that it says G effective. Okay, let's go for next one. See, we have to analyze all the cases first here so that in numericals, no, we can manage with the